Now bringing back the Jolly Rancher candies. You may or may not have had these before. Now actually in this bag specifically, there are 5 apple, 8 watermelon, 10 cherry, and 15 grape flavored candies. So typically I bring the candy to class. Sorry that you just have to look at it. And what we're going to do here is you're going to randomly select 3 candies without replacements. We're going to put our hand in. We're going to pull out a candy without looking. We're going to set it to the side. Then we're going to pull out another, set it to the side. We're going to pull out another, set it to the side. So that's the idea. This is classical probability because we have all the Jolly Ranchers in this bag. And we just need to find out what's the probability of certain things. So the first thing we're going to do is look at the probability of picking 3 grape Jolly Ranchers. 3 grape. So we have 3 events. That is picking the first Jolly Rancher, the second, and the third. So I'll say probability of 3 grape. So thinking about our multiplication rule, that's going to be the probability of getting a grape. I mean, it's the first event is going to be what's the probability that we get a grape. And I'll just put probability of G for grape. So one thing we do need is to know how many total Jolly Ranchers, if you want to take a second and see if you can add those all together. So we have 38 total candies. So 38 candies in our sample space. And we know that we have, there we go, 15 grape. So the probability that we reach into the bag and we pull out a grape. 15 out of 38, because there's 15 grape candies and 38 in the bag. So then, let's say that happens. We randomly pull out a grape. Grape's over here. Okay. So now this is what's left in our bag. So now we want the probability of pulling out a grape given that the first one was a grape. So with the fact that the grape is now there, we now realize that we only have 14 grape left. And then we also have to think about how many candies we have left in the bag. And then, because we're pulling out 3 candies, we have 3 events. We also want the probability of a grape given that the first and second are grape. Now, so if the second one is grape, I unfortunately cannot make it not random, or else I might not pick out a grape. So we get a grape. So now how many grape are in the bag? And how many total candies? And you should try that to put that all into your calculator if you can and see what comes out. Remember, multiplying fractions, you're just multiplying the numerator, multiplying the denominators, and we should get 0.0539. So make sure you can do that on any calculator and get the correct answer. Now we're still going to pull out 3 candies. But now we want the probability of not getting any apple. No apple. No apple. But we want 3 candies still. So we want the probability of not an apple. So now we're back to the original bag. We got 38 candies in here. And we want to think about how many of the candies are not apple. So we notice that there are 5 apple. So now we just want to think how many are not apple. 38 total candies, 5 of them are apple. So that means 33 are not apple. So the probability that we pick one out that is not apple is pretty high. There's one that's not apple. And then we do it again. So now we want the probability that we get not apple given that the first one was not an apple. So now we just think about how many in the bag are not apple. And how many are in the bag? And now we have our second fraction. Notice the multiplication. Okay, another one that's not an apple. And then we do it one last time because we're picking 3 candies. I think you can see the pattern here. So left in the bag are 31 that are not apple and 36 candies in the bag. And when we do that, you should be able to put that in your calculator and get 0.647. So notice this is a fairly high probability because all of the probabilities are pretty high because there's a lot of candies that are not apple. So the probability of getting 3 of them that are not apple is pretty high. There's only 5 apple in the bag. All right, done with the candies for now. So now we have a very small table, and it's the highest level of education for 50 applicants for a job. So they looked at their resumes and they said, do you have a bachelor's degree? Do you have higher than that? Do you have a master's degree? And then made a note of that. So now we're going to put all these job applicants in a bag, and we're going to pull one out, and then we're going to pull out another one. So it says if 2 of these 50 applicants' names are chosen at random without replacements, we pick out a candidate, we stick them over there, we pick out another candidate, we stick them over there. What is the probability that the first is a bachelor's and the second has a master's? So probability of first bachelor and second master. So order is actually quite important in these because it does affect the probability. So we want the first person to have a bachelor's and the second to have a master's. So the probability that the first person has a master's, we know that there's 50 total applicants. So, I mean, you're welcome to pause and see if you can get the answer to this now that we've done some examples. 50 and the bachelor, 35. And then we have one less bachelor, or bachelor's, sorry. We do have one less bachelor, but that doesn't really matter. We have one less applicant because they had a bachelor's, so they are out. And we want the second to have a master's, so 15 of those. So notice the numbers aren't going down because we're actually talking about different things here as we have the first and the second. But we multiply, put it in the calculator, 0.214. Now, if replacement was allowed, so notice that B just says, what if we put that applicant back into the bag? What would happen? And what you'll find is that if we do that, we should end up with 35 out of 50, but then that person goes back into the bag, so we still have the 50 applicants, and now we just have 15 with the masters. So when we do this, and I really should be doing this because I'm rounding these numbers, we get 0.210. So the reason that we bring up this problem is because I want you to notice these are very, very close numbers. I mean, the difference is just one value in a denominator. And so in looking at this, you can see that sometimes with or without replacement, answers are still very similar. The larger the sample size, or I should say the larger the population, the closer those numbers are going to be when you take samples and do things like this. That leads us to the last problem, the 5% guideline for cumbersome calculations. So another word for cumbersome is typically, I actually have this in the orientation, time consuming would be one way to say it. So this guideline can actually help us do certain problems. What it says is if you're taking a sample size that is no more than 5% of the population, you can actually treat the selections as being independent. So what that means is that you're saying that the probability of one thing does not affect the probability of another, which is not typical for many problems like all the ones we've just been doing. So what we're going to think about here is we're going to select, quality control is a very popular thing in business. If you're building tons of some item, you want to check them every once in a while and make sure they're coming out okay. So we're going to talk about something random, car ignition systems. And this company has done 200 of the systems. They are going to randomly sample 3 of them. So what we first want to recognize is that the sample size is 3 out of 200. This is 0.015 or 1.5%, which is definitely less than 5%. So we do want to realize the sample size being taken in the problem is very small. So they're going to check 3. And so we want the probability that all 3 systems, good, something like that. We realize that 5 of the systems are defective, so that means 195 are good. So we want to take a system out. These are randomly selected at the factory. We grab a system, and we want the probability that it's good, and that's going to be 195 out of 200, because 195 are good, and there's 200 systems. Now, then we put it over to the side. Now we're going to take out another one off the conveyor belt. I don't know. So now there's 199 systems left. And because we took out a good one, there's 194 good ones left. So this is the probability that the second one is also good. So similar to the Jolly Rancher problem. And then we, at that point, take out another good one. We have 198 good systems, or 198 systems, I should say, and 193 of them are good. So these are some pretty big fractions. We do the math on it and we get 0.926. Now, the whole idea behind this guideline for cumbersome calculations is that as long as you have this situation, which we have right here, the sample size being small, I can treat the 3 ignition systems as the probability of getting them as independent. So essentially what that means is we're treating it like we are replacing the system. So what it means is we don't think about the fact that we've taken one out. That's not part of our math. So it means that we think of the first one as being good, we think of the second one as being good, and we think of the third one as being good without the idea that one is going away each time. That's what it means to treat as independent. And then for some of you, depending on what math you have, it probably looks familiar that you're taking a number and multiplying it by itself 3 times. And so that means that you take that number and cube it. And your graphing calculator can cube things. So you can use this, the button above the division sign is an exponent. So if you press it, it'll pop you up. And so you can work on trying to see if you can make that happen. Parentheses are going to be important here, and the parentheses are just right next to the division sign as well. So if you do a side parenthesis, put in a fraction, put the numbers in, put the other side parenthesis, then use the little caret, the little up arrow looking thing above the division sign, you can get the exponent and then put the exponent on the outside of the parentheses. You should get 0.927. So the difference here is very, very, very small. Notice it's only off by 1/1000th. And you might say, well, I don't mind doing the way that we see in part A, that's fine. But if I asked you, if I said, oh, we have 2,000 systems and we're going to test 50 of them. Well, thinking about that, that would create 50 fractions, which is a ton of fractions, and you'd hate it. But if we use B, we can still only have 1 fraction. We can just raise that first fraction to the 50th because every single fraction is going to be the same in a case like this. So that's why the cumbersome calculation rule can be very helpful, again, in certain situations. And that's section 4.2.